Kurad. All right, there we go. Welcome back, everyone, to day 3 of the, let's get to the slide. Drum roll, please. Day 3 of the What's Microcontroller with Python and the Microbit workshop. All right, so previously we've talked about breadboarding and electrical connections and how they work. We've connected lights and measured them, and I think we've all got our push buttons going too. So today we are going to advance to the servo and the potentiometer and actually do a little bit more than it says here with those things. We'll also be looking over the teaching materials, the cyber.org curricula, and some of the other kits that students could potentially, that classes could potentially have students use either simultaneously or graduate to them. Okay, so getting started here. This is the circuit that I want to make sure everybody has got going. View present. So I'm going to try to get everybody in the thumbnail view. So is this similar to what you all have? Were you able to make these connections during the homework? Did you get the servo horn, this little armature to point to the different positions in its 180-degree range? How did that go for you?
It went fine. It went fine.
Excellent. Thank you, Norman. Sylvie, I heard from you before the workshop started that it went fine for you too. Anybody get stuck? Need to jump in and say, hey, I couldn't get it working. Need some tech support.
I didn't have any issues at all. I love the graphics. They're really clear.
Oh, wonderful. Okay. All right. Well, if we're all good with this, let's go ahead and move on. I am going to take just a short step back, and then folks, jump in and stop me if I already talked about this. Let's see, got to get out of the present mode. Okay, so I don't think I went over just a few things I wanted to point out within push buttons. So I'm going to hit that just very briefly before continuing on to more about servos. So every time in the parts list section, when there's a new part, we introduce it with a picture and its schematic symbol. So that's a pattern that you and the students can expect, is that, you know, we've been using resistors quite a bit already and jumper wires too, so we don't need any pictures of those anymore. But this is the first use of the push button. So here it is with picture and schematic symbol. And actually, I should mention that before that, you may have noticed that there's a setup from previous tutorials. So basically what this does is it says, okay, well, we're assuming that you finished through the LED lights chapter. And so here's what you should be starting with. If you have that, just skip to the next activity. Oh, pardon me. Otherwise, get started here, and there's actually details of all the parts that appear on here and which link to follow to test each one.
Could you share the screen, please?
Oh, my goodness. Yeah, so I'm going to have to rewind a little bit. Thank you. Yeah, I didn't mean to not be sharing the screen. Let's see. Share screen. Screen 2, there we go. All right, so let's back up just to okay, so I'll restart from here. So in the push buttons, it shows the circuit from the activities that have led up to it. And so basically, if you and your students arrive here having just finished the last activity in light blinking, you're just ready to skip to the next activity, which is here, build and test a push button. Otherwise, we've got the nice little picture and schematic, and then actually links to go to. And following these links, you can test each little piece of this setup before continuing into push buttons. And the reason we do that is because we want to use the push buttons to control the lights at a certain point. But before that, it's always very step-by-step. We're going to build and test the push buttons. And so this is that first instance picture of the new push button part, because all the rest of the parts are going to be familiar at this point. And so that's what we do on first use, is make sure to include a drawing and schematic symbol, and talk a little bit about what these numbers around the drawing are and what they mean. They're pin numbers so that we can use them for reference later. Then this is a close-up you're probably familiar with. It's something that after seeing a number of teachers at workshops and students in classrooms, rotating this by 90 degrees and still succeeding on inserting it into the breadboard, we made sure to show them, hey, you got to check that push button to make sure the little legs are sticking out of the side before you insert them into the socket. So once you've done that for one push button, this is a schematic, and notice, see how the other parts of the circuit are still there but grayed out. That's another thing we do since we're building on this circuit, just as a cue to people who are following along, not to remove those parts, that they're still supposed to be there, but that we are focusing on this green light and this push button. So then we move on to say, okay, well, here you've got your push button and your light. So let's test and see if the push button can control the light. And so while we're at it, I'll just have you guys load this in. Let's see here, chat. Okay, so I just chatted you this script, and we'll have you just load it and run it. And the goal here is just going to be to hold down the push button and verify that the green light's connected to P13 stays on while you hold it. Oh, I'm sorry. The goal here is, I got ahead of myself. The goal here is to see the zeros and ones depending on whether or not you've pressed the push button. So I'll go ahead and demo that. And hopefully all this code flashing and et cetera is familiar from the earlier workshops. But the important thing is after you've loaded the program, so you're connected, flashed, and then open Serial. And what it'll show while you're not holding the button down is state equals 0. And then when you hold the lower button down, the one connected to P6, it'll show state equals 1, and then release again and state equals 0. And this opens opportunities for the idea of lessons in binary values and how an electrical condition can be interpreted as a binary value. Everybody good? Can I move on? All righty, excellent. And then again, just jump in, unmute yourself, and give me a shout out if you want to slow down to get something done. The push button circuit, since I was a junior in electrical engineering school, and when our prof first showed us how a push button worked, I was scratching my head for a long time trying to figure it out. So this tutorial goes to some lengths to try to help illustrate what's happening with a push button. And so one thing is, very simply, when you release the push button, pin 6.read digital gives you 0. When you press it, pin 6.read digital gives you 1. And that 1 or 0 value gets stored in a variable named state. So that's one point about this picture. Another point is basically when you press the push button, it shorts this row to this row. Well, the upper row happens to be receiving 3 volts. The lower row happens to be getting ground, but with a large resistor in the way. So when you press and hold the push button, all this 3 volts appears where the red is shown, including right at the P6 node right here where it goes into the microbit. And so then it shows, hey, the microbit stores a 0 when you're not pressing, and it stores a 1 when you're pressing. So this is one of those that has an MP4 that you can open up and pause it at each change in this clip and talk about what's happening. And then there's also some leading questions. So basically, we want the students to take a look. This is trying to guide the students to take a closer look at, looks like we need to remove a parentheses there. I always see things like that when presenting. This is designed to have the students take a look and discuss with the teachers, with you guys, what they're seeing in this animation. And then the solutions are in the teacher's guide. And then it talks a little bit about the script and what's happening. And so it's, and then there's a try this where instead of printing, we go ahead and use the result of pressing the push button, which is a 1 or a 0 that's stored in the state variable. Well, that same state variable that stores a 1 or a 0 can be made to turn the light on or off. And bear with me just a minute. I need to hunt that script down. Actually, okay, so let's go ahead and just change it on the fly. So folks, do you all have a print statement on line 11? Go ahead and put a hashtag to the left of it. And then also put a hashtag to the left of the sleep. And then after that, all we need to do is say pin 13.write digital of state. So instead of putting a 1 or a 0 in there, we're just storing what's read on the push button and recycling it in the statement that we've been using up till this point to turn the light on and off. So when we flash that, and I'm going to stop my video and move the camera over to my setup so we can take a look at the results. All right. So when I go in and press and hold the button, the green light comes on. When I release it, green light goes off. That's, the text also talks about how that's part of a loop back connection. Was that visible to everyone? And were you able to make it work in your system? Excellent. I'm getting thumbs up, but I also see a few heads down. So I'm going to wait for just a second. Again, for those of you who are still working on it, we are commenting the print statement by putting a hashtag mark to its left and commenting the sleep statement by putting a hashtag to its left, and then adding pin 3.write digital of state, where state is in parentheses. And then after being connected and hitting flash, you should be able to press and hold the lower of the two push buttons and have the light come on. I'm going to make a few other modifications here. And I'll just paste it into the chat this time. So we don't always want to use a variable, even if we've got it inside that argument. So here's an example where it's better not to have it. And this is from the your turn section. So this is the next thing that the students are asked to do. But since it's in a screen capture and you can't get it easily, I'm going to just paste it into the chat. So go ahead and try that one. I should probably try it too. Okay, I didn't do that correctly, apparently. I'm just getting a constantly on light. Okay, let's see what the your turn section actually says. So if state is 1, oh, pin 13 is probably what I did wrong. No? Print state, if state equals 1, then do all that.
Andy, it's your indents, I think.
Could be. Although I'm not immediately seeing an indent problem. This is kind of a good little exercise, having everybody watch the debugging process, because you and your students will be doing a fair amount of that to find the mistakes.
When you get a chance though now, can I see that? Yeah, the setting of it.
Okay, I'm just going to do this verbatim here. Is anybody else getting their light to blink?
On my side, the green light, the green LED switches on, but doesn't go off.
Okay. What on earth did I do wrong here? Okay. I accidentally switched languages. We support quite a few languages here at Parallax, and I threw in pause where I should have had sleep. Okay. So now I will pass you the correct script with apologies. There you go.
I'll say sleep too heavily or too often at the end of a Friday.
That's a good point. Let's see. I will say caffeine or cafe latte or whatever your favorite is.
Andy, what am I missing on my breadboard?
Okay.
It looks a lot like yours.
Pin, stop share. Okay, so go ahead and hold it up a little higher. So, yeah, I don't see the servos, but you've got your, oh, there it is. Goodness, sorry about that.
And it worked.
Okay, excellent.
Okay.
So, no, everything looks right. It looks like you might need a potentiometer down at the bottom, but we'll get to that in a bit. So is this working when you hold the button down?
No.
Okay. Did you try the most recent code I pasted in?
Oh, okay. Let me do that.
On my side, it's flashing now when I hold on.
Okay. Excellent. Thank you, Sylvie. And share screen. Okay, so what you see here is what I pasted in. I should probably change this comment, but that you don't need to re-copy anything. Rosa, would you like me to paste it in a second time?
I pasted it, but it's not doing anything. Do I need to put the batteries on?
Not for this in theory. I think what we may be getting with you is try pressing on the resistors like you did to get things to work the previous session. I think you've got a loose connection somewhere.
Okay, I get it. Okay, now the green one is blinking if I press the button. Is that what is supposed to happen?
Yes, it is. And so what else is happening, I think, is that the little wire ends, there may be one or more that have not sunk far enough into the socket to actually make a good connection with the metal that's underneath the plastic. And when you put your hand on them, I think that's what's correcting it.
Okay. So is it only the green one? It should be on?
Just the green one right now.
Okay,
yes.
So then it's working. Thank you.
Okay, excellent. And then somebody else had a question.
Andy, I had a lot of problems with those resistors because they're about an inch shorter than the ones I have here, and they were really a tight stretch. And I found that they would come loose out of the socket pretty easily.
Yes, this is the supply chain disruption at work. So we did quite a bit of due diligence to make sure that something like this didn't happen, but it happened. And we're actually behind the scenes trying to sort out how to correct this.
I have a whole pile of, I have literally thousands of resistors I've been collecting over the years. And the ones I have here, the leads are about an inch longer than they.
Yeah, and our leads are normally at least a half inch longer than that. It's a very comfortable run with the normal resistors that we get, and we basically had to move quickly or not have any resistors with the
I was
supply
about
chain
ready to
stuff.
put in some extra jumpers and stuff like that, but then I found my resistors. Like I say, they're at least an inch longer. Yeah,
and I'm going to be making some adjustments to the pictures of how to connect the stuff so that the runs aren't quite as long. The main problem is that red LED up top. That just is cutting it too close. and maybe even the yellow LED. I may just need to scooch everybody closer together. Some of that's going to depend on if we can get the longer LEDs moving forward. So anyway, yeah, that is a supply chain disruptions gotcha right there. And we're trying to figure out what to do to make sure that everybody has a good experience now that they've got those resistors in the pack.
Well, and the thing is, Sandy, you added in your comment to bend the ends.
Yes.
And that's been working pretty well to do that. It's short, it's nice. The resistor is laying down flat on the breadboard, but it's working. So we're able to do the contacts.
It's working for me too. I'm concerned about everything worked okay except for that dratted red LED. That's just too long of a run. I mean, it worked for me, but I kind of know what to do, and I'm afraid that students who are not in that position might not have the best experience. So we're going to figure out what to do to make that better, and I'm not sure what the answer is quite yet. But rest assured, we are working on it. We'll make it work for your class. That's student success is definitely our top priority. And so the documentation has to make sure that they can do these things. That's one of the reasons, or what I'm hoping you discovered overall from the homework was that it was pretty easy to follow along and build the circuit, write the script, do the tests. We always want that to be something that the students can succeed with so that they can then have some enthusiasm to go into learning a calculation or a concept that they'll get quizzed or tested on later. Okay, let's see. All right, so the only other thing I wanted to talk about is inside the push button, which is, and we'll skip this because we've already taken some measurements, and I hope we take some measurements in a little while as well. So here is the same circuit, but with probes added. So the P2 probe is sitting over here where the light gets turned on and off by the microbit on P13. And then the black probe is over here in ground along the left. And so here we run a script where you can actually see the push button going high and the light turning on and off. And I'll just show you what it looks like. And of course you can download the script. Oh, I'm sorry. So we actually started with, I faked myself out with the wrong picture. So we're starting with this, but in the circuit area, we're adding a push button and then connecting probes to it. So forget what I said about measuring the blinking light. So we're starting with a second push button and the meter probes connected to it. And then downloading our friend continuity tester, which we've used before. And so what happens with the continuity tests is that there's a whole bunch of different column and row coordinates, which pretty much correspond to so for example, this first set of column row coordinates where we start is connected to the rows for the upper pair of legs and the rows for the lower pair of legs. And what the instructions are guiding the students through is saying, okay, well, now that we're looking at whether these two probes are connected or not, because we're running the continuity tester script that we tried earlier, gee, is it connected when we, are we getting the check mark in this little display right here, or are we getting the circle with a slash through it? That's the big question. And so the students actually go and they say, okay, well, I'm not pressing the button and I've got the circle with the slash. Now I'll press and hold the button and I'm getting the check mark. And so they can see that by pressing and holding down the top of this, the little, I don't know what to call it, the little pressy thingy on the top of the push button, when they hold that, that actually creates an electrical connection between this upper row and this lower row. And so that's what happens in scripts and tests, is they get a whole bunch of battleship coordinates to try with those red and black probes. And then to reinforce that, we talk about, okay, you just ran all these tests. What was happening inside that little box O push button that you can't see? And so here we are in the not pressed state. And when the button is not pressed, the contacts, this little metal bar, is floating above the two legs of the push button, which as we look at it in a translucent way, you can see that the leg actually is a wire that passes all the way through that little case of the push button. So when you press and hold the push button, then the little bar inside, underneath the part you press, comes to rest on those two legs. And so now you have a metal, a conductive metal connection, so that so that current can flow through here and out there, or vice versa. And also voltages will be detected here. If you don't have it pressed, if there's some voltage applied here and a different voltage applied there, well, they'll measure as different voltages. And also your continuity tester will tell you, hey, these two legs are not connected. Likewise, these two legs are not connected. And so that's the test that the students did, is with it not pressed, what's connected, what's not. With it pressed, what's connected, what's not. And so hopefully with that, it'll demystify how the push button works. Okay, any questions or discussion topics before we move on? Anything? Okay, everybody looks happy. Okay, excellent. All righty. So next up, I do not remember if this part was, if I brought this part up while I had forgotten to share my screen. So have we looked at this yet? Okay, so this looks new to everybody. However, we don't want it looking too new, because this is everything from your homework. Basically, the lights and the push buttons that you built between Monday and Wednesday are built up in this area right here. And then the battery pack and the servo that you added are built up here. And then the picture of the potentiometer is down here. And so that was the last thing on the homework due for today. And so how are we doing? Does everybody's board resemble this in the presence of the circuits? Are we good? Thumbs up, nodded head, thumbs up, thumbs up, thumbs up. Okay, excellent. All right, that means we are ready to look at some interesting stuff in servos. So we are currently still adding material. I just moved to the top page. So this is like basically the book cover of What's a Microcontroller with Python and the Microbit. So these were some of the tiles you went into, the writing programs, the computer microbit talk. And then we did the setup together, talked about the electrical measurements, did the lights partially in homework and partially during the workshop, and even with some overlap because I forgot what I assigned you. Sorry again about that. We just talked about kind of some of the key things in the push button chapter, and it goes on to do some more elaborate projects. If time permits, we can come back and try some of those, but we also have some fun, elaborate projects ahead of us. So even though this is the last one here, there's a lot more on its way. And so what I wanted to show you an example of next was something that is going to be flowing up to the site, currently scheduled to start happening next week. And pardon me while I sift through my links and find the right thing. Okay, it's coming up now. This is servo position control. And so this is the working document for servo position control before it gets harvested. And it gets harvested and it goes to a couple of different places. So for example, all of this is basically web ready. So we have a little illustration, for example, of how the signals, which are like turning the light on and off, just happening much faster so that the eye cannot see it. These high and low signals are sent repeatedly to the servo, and then the servo armature assumes a certain position depending on actually the width of these pulses. And so that's what we go through. And I think that you guys all started, so we had the setup from previous activities again, which I had you skip because I'm confident that all of you basically already have your lights, your push buttons, and your probes. So I started you right here and we did the battery. And so we went through the battery, so you should be good on all that. And notice that there's some questions that are crossed out. So every other question is crossed out here. And likewise, in any exercises and projects, we have every other one crossed out. And the reason it's crossed out is because Nicole Litterer, who will be speaking later today about the teacher resources she works on, created these and then harvested half of them for the teacher's guide. Okay, we also did connect the servo, and I take it everybody did okay with that. You got your servo armature to move. Okay, let's see. One more time, nodding heads, thumbs up. Excellent, all right. So we got a moving servo. Do you think the students are gonna like that? Is that pretty cool? Does that have some fun value? I'm getting I'm getting some nods from folks who are really familiar with them, but all right. How do you like the close-ups? Did they work out? Was this close-up clear enough? Okay, good. Excellent, 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 excellent. Okay, so we got the servo moving. Let's talk about some other, okay. And so let's see. Yeah, so the tests, in addition to simply having the servo move, we have some opportunities to talk about things like angles and, what is an angle? How does it look on the coordinate plane? How can you superimpose something that's on the coordinate plane to something that is a physical thing? And so, so that's what this partially explicitly and partially implicitly gets us there. And we talk about degrees and what is a degree and what is angular position. Also, we talk about, hey, when we said pin 16, right analog 26, it was over at 0 degrees. When we changed that 26 to 51, it goes to 45 and then 90 and 180 as the value keeps on getting larger. And that value is kind of a mystery value at this point. But this animation talks about the result of that value, that when we use 128, there are 2.5 millisecond pulses that are sent. When we use 26, it's half a millisecond. When we use 51, it's 1 millisecond. When we use 77, it's 1.5 milliseconds, and so on. And the idea, what this opens up is the opportunity to, first of all, reinforce what we talked about the high time and the duty cycle that was introduced. I spoke briefly about it. When you go through in more detail, you will see more about duty cycle in the electrical measurement. No, I think it's the LED lights chapter, because we start out with measuring duty cycle in a signal that you can see, and we measure it on the oscilloscope so that hopefully by the time the students get to this point, this is something that's innately understood, because they will have measured those digital on-off signals in 2 different activities before they've gotten here. So when they see this, the hope is that they'll understand that, oh yeah, it's what I've been doing. It's just that light would be blinking so fast I cannot see it. Let's see here. Okay. Another opportunity with this is those mystery numbers. How can we demystify them? And it turns out that it has to do with functions and y equals mx plus b. And so it guides through solving for y equals mx plus b. And then that gets put in a script, and the students can run that script, and then they're challenged to do the inverse of that script. So they can run a script which will tell them, okay, so here's the script that they run. So when they enter a value that was used in the script, those mystery values of 25, 51, and et cetera, what is the degree equivalent after they did that little y equals mx plus b exercise? And you can see that we're close to 0, 45, 90, and 180. And then the challenge to the students is, okay, well, we introduced more formulas before getting here, so that you can rearrange the formula so that if you give it one of those mystery numbers, it will give you the corresponding degree value that the armature should have turned to. And then we have more harvested questions, exercises, and projects. And then we do the button control. So let's go and do something fun now. I'll give you this little piece of code. I don't know how many of you worked ahead to try this. And also I need to watch carefully, because there is a limitation on how much text I can paste in one shot. I think I got you the entire script. So go ahead and try that one. And so this is push button control of the servo. If you press and hold one button, it's going to rotate, the armature will rotate counterclockwise until it reaches 180. And if you press and hold the other button, the lower one, it'll rotate clockwise until it reaches 0 degrees. I forgot to plug my battery in. Make sure that you've got your battery plugged in for this one. Otherwise, the servo won't respond for you. That was the lower button. Now I got the upper button. You can let go at points. And then you can keep holding it, but it'll never go past the endpoints of its range of motion. We all got that going? Okay, thank you. All right then. And then do, again, shout out, slow me down if you need a second to keep going. Or to, yes.
And all it was supposed to do was move like a tiny bit, right?
Well, so it only moves half a turn. So when you press and hold one button, it may have only moved a tiny bit. Then try pressing and holding the other button, and it should move. If you keep on holding it, it should move half a turn.
Okay.
I can hear it.
Yep.
Perfect.
One moves. Yeah, okay. Thank you.
You're welcome. And then now that you're over at one end, press and hold the other button. Make sure you can go back to the other end.
Oh, okay.
And it looks like a number of you are in the document right now, and that's good. I'm going to copy and paste a link of this document to the chat log. I should have done that. Share. You don't need to be in it, but I want to make sure that that link is here. Okay.
It helps when we're using two different devices. I have the presentation in one computer and
yes,
the other on the other. So I'm copying from the document. I can't copy from the chat.
Okay, sorry about that.
That's okay. I worked around it.
It'll keep you on your toes, that's for sure. All right. So there is a link to the doc, especially for those of you who are doing like Sylvie. Okay. So let's try some other fun stuff like servo tilt control. Oh man, I don't have the link to the full length one. All right, I guess we'll just look at the zoomed in version here. And I will check with our web publishing person to make sure that you can all get to the high resolution version. So this is going to be the slightly fuzzy approximation of the high res version. So you're holding your board like a steering wheel in front of you for this one. And so when you run the script, basically you'll want the armature, the horn, in servo speak, it's called a horn, to be pointing upward as you rotate the system as shown here. And then I'll get you the script for that. Copy. I think this was the one that I introduced on Monday. Okay, pin 16 right analog. Okay, so you have the whole script right there. And for those of you going in the document, you can Control F and type in servo underscore points underscore up, and that will get you straight to this code example. And
it's crazy when I did that. It was like moving a bunch and flickering LEDs. So it went a bit nuts on my table when I loaded.
Yeah, when it's sitting flat, the script has some challenges figuring out which way is up, because it really needs to be held like a steering wheel vertically. So yeah, thanks for mentioning that, because it's true. Some students will probably find that to be either mysterious or exhilarating, or I'm not exactly sure what. But yeah, these are so I've been showing the results on the screen of what you want to see with the little compass needle / clock hand pointing up, and the armature also pointing up. You don't actually have to hold it vertically. I'm holding it kind of at about 45 degrees, and that's enough to be able to steer the servo like this, so that it always points in the same direction. It's a pretty slick little application, I think. And then here is the servo freaking out, like Sylvie mentioned. So much so that, one thing you can do is if you add continue right below while true, below an indented, and then reload the code, that will stop your servo from shaking without having to yank the batteries. Although yanking the batteries, rather unplugging the battery pack from the system is important when you're not using it, because otherwise, even when it appears to be sleeping, it is going to drain your batteries. So it's important to unplug them when not in use, and that's the tutorials make a big to-do about that, and step-by-step instructions say every time. So if you add continue, basically this script just kind of cycles in this area, and it never makes it to any of the built-in accelerometer and set the angle of the servo arm. Just does these two statements over and over again. Continue says jump back to whatever loop you're in and repeat from there. And then when you want to rerun it, just make sure to comment out continue and then flash it, and you'll be back to running your code. Sometimes students put something like this in here and then forget about it and save a copy, and they wonder why things don't work. And well, I've actually done that to myself a number of times too. So not just students. Okay, how's that?
And the only did was the thing is moving, right?
Yeah, when you have it sitting flat, it's gonna move a lot, because it can't really figure out which way is up until you start holding it vertically like a steering wheel.
But the lights were not supposed to do anything, and I'm looking at
that's correct for this. Okay, that's correct for this. The lights are just there for show.
Okay, that's all right. Making sure that they were supposed to.
Yep. Now then, got 10 more minutes, and then we'll have Nicole talk briefly, or actually closer to 5. All right, so this is a fun one. I'll give you a link to the script to download and load. So what we're going to do now is measure the servo signals using the Cyberscope. And so I want you to go carefully with me on this one. Let's see, I need to get you a link to the script. Here it is. Okay, copy link address. So I'm going to give you the link to download the script hex file. And then you'll be dragging and dropping that downloaded hex file into your python.microbit.org editor. All right, so I'm pasting that script link. Sylvie, that's in the, and anybody else who is doing this, we're in measure servo signal with, oh, Sylvie, you already did it, but anybody else who's doing it like Sylvie with 2 machines, we're in the measure servo signal with an oscilloscope section, and the download for the script is in the script section. And so you'll click it and then right click the link that appears, copy link address, or you can even open it in a new tab and download it that way. So this is the other option, just downloading from from the tab like I think we were doing that previously as opposed to pasting it into the window, but either way works. Paste. Download. Okay, then go to microbit, python.microbit.org, and open up the script by dragging it onto the editor window. And then now this is important. Folks, we need to flash it first. And I'd like to ask that everybody not work ahead. We want to do this one in lockstep. So step one is just to flash it to your microbit and don't go any further yet. And we especially don't want to hit connect when we get the Cyberscope open. So everybody, the servo plot script, go ahead and flash it into your microbit. It's going to make the servo armature turn to those 4 angles, just like the test you ran for the homework. Then it'll be really important to disconnect from your microbit in the editor. So disconnect. So if it says disconnect, then hit it and it'll show an open connection with the connect option visible. So once we're disconnected with the Python editor, then we want to go over to, I forgot to show you about the circuit, so we'll have to jump back to that in a second. Actually, we need to do that first. So we'll just let the microbit do its thing and talk about the circuit. What we need to do before this is to set the alligator clip. Use the red alligator clip to connect the 3-pin header on P2 to the P16 row. It's going to be breadboard row 14 in the left terminal strip, and then it's the same row of 5 that the edge adapter's P16 pin is plugged into.
It's E what? It would be E what?
Okay, so so down below, you should have 2 3-pin headers, one connected to P0 and one connected to P2. So it's just the red, oh no, and for you, we're not using the red cable because you had a bad red cable.
Yeah, that's fine.
Okay,
I know.
A cable of your choice that's not red.
Yes.
Go ahead and grab on to all 3 of those pins in the 3-pin header that's connected on the same row as P2.
I have that.
Perfect. Then on the next end, the little jumper wire that you have gripped on the other alligator clip, you want to go ahead and plug that into the same row as the edge adapter's P16 pin.
P16 or E what?
It should be P16. So right here where I'm waving my mouse, it's going to say P as in Paul 16.
Yes, I see.
Yeah, perfect.
So they have to share the.
Yeah. So what we're doing is the P16 with our script, it's making it send a very rapid on-off signal that we could not see if we connected a light to it. The light would be going on and off. It's just our eyes would not be able to register it. But our measurement equipment here with the microbit can register it. And so we're just going to measure it with some equipment.
But I'm having a hard time like inserting it. It's like not enough space.
Try the next one over.
Okay. So that would be P15?
No, the to the left as opposed to vertically.
I get it. P16, right?
Yeah, any one of that row of 5. Okay, if it will it go into?
Okay.
You got it?
Okay. Yeah, I got it. Yeah, I just thought it had to be in the. Never.
In that particular, no, any of those 5 is fine. Okay, now let's see. And then we've got our scopes software running. I need to get back to that on the screen. Okay, here we go, I believe. All right, so go to cyberscope.com or cyberscope.parallax.com, but no further, as in don't click connect. The reason I'm saying don't click connect is because we're currently fixing a bug in this where if you clicked connect with the default settings, it would overwhelm the some Chrome browsers. And so, we just want to be here. Do not click connect yet. First, select your device. Okay, so I want to make sure, we got to make sure everybody's on the Cyberscope. Have you all got the Cyberscope open? Cyberscope.parallax.com. Okay, excellent. So once we're at cyberscope.parallax.com, click the device and select oscilloscope. And then once you've selected oscilloscope, you should see a blank screen. That'll be good. Then in the time per division drop down, select 5 milliseconds. So we've been up here previously in the 1,000, 500, 200 when we had human speed things that we were looking at with the LED lights. So now we're down at low electronic speeds with 5 milliseconds per division. Now, once you've done the 5 milliseconds per division, you're safe to hit connect. And then make sure to pick your microbit if you have more than one serial port. And then you should start to see some activity on the screen, and basically wait for the servo to go to a new position and then click the trigger drop down. And for me, yeah, I thought I'd gotten this fixed, but as you can see, my Cyberscope is still stalled. And the reason for that is because it's sharing processor time with my video and my Zoom and all that other stuff. And that may be the case for you. If you can, at this point, click trigger. I'm just going to kill the page and restart and hope for the best here. So these are issues that we actually have several people working on to make sure that it's pretty bulletproof before the students get to it. All right, so I need to go to oscilloscope, 5 milliseconds per division, connect. And then after you've connected, go to trigger. And if you can, hit rise. It's freezing on me. Is anybody else having freezing problems with their Zoom and the video and all that? Okay, so you're all good. It's just me, huh?
Mine works okay. Mine works okay.
Okay, yeah, my Chrome just completely stopped. I think probably also there was a giant list of animated GIFs in that Word document that I had open, so it was probably choking on that as well. So I'm going to close all other instances of Chrome and see if I can get this to display. Okay, so don't restore. Oscilloscope. For those of you who were able to get the trigger set to rise, do you see the, I'm going to preset mine to rise and see if that'll save me here. Okay, it looks like the information is safely being buffered and should show up. Oh no, I have to set. So you set your trigger to rise and your channel to channel 2. Yeah, I sure would like this to display for the YouTube video. I'm glad to hear that all you guys have it going. Okay, let's do 0.5 millisecond. And
And if I got this correct, every time it moves, it kind of like widens.
yes, it does. There we go. Managed
Why
to.
is that?
Okay, so I have it going. And again, we are working on this. There are several different groups that are working on making sure that this is that the kind of thing that I had trouble with as a Zoom presenter with too much open on, that was in the Chrome browsers, that it won't freeze up. But okay, so you're seeing that basically each new position of the servo results in a wider pulse. And this wider pulse here, this wider high point, if you had an LED light connected to it, the light would be on during that time and then off during this time. So on for just a little bit of time, then off for a longer little bit of time, then on again. And notice that each time the servo armature gets closer to 180 degrees, it's in response to the on time, the time the light would be on, lasting longer. And this is the signal. What we're doing is we're using equipment to look at an oscilloscope to look at the signal that the microbit is sending to the servo to actually make it do that. Fundamentally, it's like a blinking light. It's just that it's so fast that all we would see is maybe a slight difference in brightness of a blinking light if we connected an LED light along on that same servo pin. So what we're doing is we're probing it with this oscilloscope tool here. And this is a very common practice in the electronics field. And so I wanted everybody to see it. And so we have the trigger set to rise, the trigger channel set to 2. And now you can, for example, move everything around. And each time the servo hits a new position, it'll refresh. I like to go over to 5 milliseconds at this particular zoom level. Now you can take a closer look at that by setting the time per division to 0.5 millisecond. At 0.5 millisecond, you see the actual width of this pulse. So here it is at 0.5 millisecond. It's from 0.5 millisecond to 1 millisecond. Now 0.5 millisecond to 1.5 millisecond. That's a delta of 1 millisecond. Now we're at 1.5 milliseconds. And then for the last position, 180, we're all the way over at 2.5 milliseconds. 3 minus 0.5 is 2.5. And so this is a way to use an electronic instrument called an oscilloscope to examine the signals going from one electronic device to another, since we can't actually see them. And so this is an important activity. And we won't have time during the main thing, but I will be sending you links when we do the potentiometer. Actually, I'll just demo it. No, I won't demo it for you because it might not display entirely well. And so we'll just leave it at this. I do want to emphasize that this is kind of a big deal. The microbit has not otherwise been used at this level of electronics intro before. I am not aware of any other microbit-based oscilloscope where basically the microbit is communicating values to an oscilloscope. And also it's really cool that not just blinking lights, but things that are happening at a high speed can be captured and displayed using this system. So it's a very powerful education tool. And if you were purchasing oscilloscopes for your class, the price tag would be jaw-dropping, whereas this little virtual oscilloscope with your $80 kit, geez, that's a great deal. And it's an important thing. I want everybody to be able to have this experience, not just, now I know that some of you have oscilloscopes in your labs already, and that's great. You may not need it, but I'm trying to kind of widen the access of this to classrooms that don't necessarily have it. Okay, how's that, folks? Okay. Well, cool. Now we have a brief presentation. Hi, Nicole. How you doing?
I'm good, Andy. Hi.
Are you ready?
Sure.
Okay. Nicole Litterer has been writing the teacher materials for this, and she's going to talk with you briefly about what you can find there. A little bit about Nicole. She is an Iowa native. And she has, now in your explanation, do you have actually two different master's degrees? One in teacher learning and the other in educational leadership? Okay, that's cool. I misread that the first time. Sorry about that.
Okay.
Yeah, and then you also work as an instructional coach supporting classroom and teachers through about practices like instructional delivery, lesson design, standards alignment, and assessment. So you're really much better than me at creating this stuff. And so thank you. Nicole also keeps me in line because engineers can be hard-headed sometimes, and making it the material educationally correctly presented and ordered and formatted and not jumping too large of skips is something that we trust Nicole with. And so a lot of the comments in that servo doc are gone now, but I was prompted to adjust quite a number of things before what you saw today. She's also working on her doctorate in continuous improvement models and has been doing curriculum in the form of assessment materials and standards alignment and what else, Nicole? Assessment.
That's good.
That's about it.
Yeah.
Okay.
That just sounds like a lot.
Yeah, I don't know how you can do it all.
I don't know. It's not that. It's not that much.
Well, that's easy for you to say. I think I'd just basically explode from having drank too much coffee to keep it all going at once. Anyway, so yeah, if you could show us a little bit about the assessment materials and standards alignment and whatever else you have ready to show the teachers, we'll appreciate it a lot.
Yeah, I will be happy to. And I will keep it brief. Oh, good. I can share my screen. Awesome. Thank you.
Oh, thank you, Bonnie. You probably couldn't just a minute ago.
No. Okay. Awesome. Okay. So I'll just show you a couple of the things like Andy mentioned, just how we're working together to try to make this happen. My background is not in electronics. I've learned a lot, computer programming as we've gone along. My son is into it. So oftentimes I ask him questions and things. So he helps me with that kind of thing. But anyway, so just a couple of ways that we go back and forth. As you can see here that there's this start of the teacher's guide. So we go back and forth quite a bit about, what should be in the teacher's guide and what do the teachers need as support, with their ranging level of abilities to be able to effectively teach this content to their students. So those are just some of the kinds of things that we talk about as we go through these. Again, here, there's just a few more questions about, our process of going back and forth. But what I think you really are probably more interested in is,
but briefly before we do that, what I'm hoping to do is, because obviously Nicole has a lot going on already, is to open it up to a wider discussion. So for example, in this servo document, Nicole, Stephanie, who was here on Monday, and I have already gone through it to the best of our ability. But Sylvie, for example, corrected me on a few things she found in the document. And so we'd like to open the comments up to a wider group after we've given it our best shot, because I know just from past experience that no matter how many times 2 and 3 pairs of eyes look at something, we don't catch everything. So, so if you're interested in giving a look at this, basically what'll happen is it'll go to the web, but we'll also open it up for comments. And then when we see comments in this Google Doc, even though it's already on the web, what we can do is say, oh, okay, that's a good comment that needs to be revised now. That's a difficult comment that will require, you know, a much more involved revision. And so we'll have to think about how to approach it. And so I'd like this document that's just about ready to go to the web to continue receiving teacher feedback. And so if you're interested in providing that kind of feedback, send me an email and I will add you to an emailing list, letting you know when the document's ready for everybody to have at with. Thanks, Nicole. Sorry about that.
Yeah, no, that's okay. I'm just going through my mind like, oh, shoot, what did I miss? I missed
actually,
what did I do?
Oh, there were 2 extra spaces of indentation in one of the example programs back in LED lights.
Oh, gotcha.
It's kind of hard to see.
All right, fair enough. So you can see the, let me scroll down to some of them. And Andy, I think you said you already showed the, here, I'll do it this way, the questions and exercises that are in here. So half of these go to the web, and then we pull the other half out into documents. So students can see the ones that are on the web with the answers that are built in there. But the other half, like I said, come to these documents that, Andy, are on just in the teacher resource pages, right? Of the
yes.
website.
Yeah, that's correct. So that is why we had you all be able to log into learn.parallax.com, is to be able to get to those resources.
Yeah, so there'll be another set that is very, very similar, but not the exact same questions to what the students can access on the website. So if you want to do some type of quiz, formative assessment along the way, you'll be able to find, like I said, kind of mirrored questions in these documents that are there. So they're listed here with the questions, so you could print those off, and then the answers will always be down below. We'll separate those so that you can use them in that format. We also have, I'm going to move your guys' photos around here a little bit. So the teacher's guide, that's okay, includes standards, and we have used the K-12 computer science framework. And these are fairly broad standards and connections, but they are connections. So you can see I've listed all of the standards in ways that they might connect some way to the tutorial, someplace in the tutorial. I'm just going to keep scrolling. And then the California K-12 computer science standards are in here as well. It doesn't say specifically how it's connected or to maybe which chapter in the tutorial the connection is. It's just somewhere in the tutorial. And then the California Career Technical Education Model Curriculum Standards, it's a mouthful. The Anchor Standards, and then also the Pathway Standards for the Engineering Technology Pathway are in here. So each teacher guide starts off with standards. And here you can see the ISTE standards are in here as well for the students. There'll be a summary of the tutorial. The one we're looking at here is Sense button presses. This one is finished, so that's why I decided to grab this one. So there's just a short summary of the tutorial. And then if there's any background or technical information that would be helpful in teaching this tutorial, I've tried to put some information there. Especially, like I said, I'm not, my background is not in technology and electronics and computer science. So if I think, oh gosh, I didn't know that was something I had to look up or something I had to ask Andy about, I try to put those kinds of things in here to help make teaching the information easier. For example, a pull-up resistor. What is that? I don't think a lot of people would know what that was. So I added that in here. There's some tips on teaching the tutorial. For example, if there are times when there is a warning inside the tutorial, I try to highlight that here. For example, there's one here about using this resistor and what happens if you don't use it. So if there's something like that, we want to make sure that the kids don't do. I try to include that in here too. There's some differentiation options and extension options. If you have kids who need additional support, in order to access the material, or if you have kids that are flying through it, they've got great background knowledge and you're looking for some extension ideas. I have some of those in here as well. And then the activity outcomes for each activity, I pulled them out of the tutorial, the web tutorial, so that you can have them here in one place. And then the student self-checks really follow from the outcomes that you see up here, but they're just questions for the students to ask themselves so that they can self-assess at the end of the tutorials. And there's one for each chapter, I guess. That's what you're calling them, Andy, right? Chapters inside the tutorials. Maybe I don't have that language right.
Okay, I have been referring to them as chapters, but we may end up going through and doing a search and replace. Okay. Tutorials has been used in the past, but since these are more information intensive than a lot of the more topical stuff, I kind of shifted from referring to them as tutorials to referring to them as chapters.
Gotcha. All right. So chapters, subsections, the smaller portions anyway. There's a section on tutorial vocabulary. So vocabulary that the students may or may not know. And that's also broken down by those chapters, sections, whatever we're calling them. So if kids want to study that, or if, again, as a teacher, if you need to reference the vocabulary. And then for some of the activities inside the tutorial, there are scripts that are outside of the Your Turns. The Your Turn, those are in a separate document. So if you're going along and there is something that the students need to do that is outside of a Your Turn, you can find the answers, the scripts for those inside of the teacher's guide. So that is what you'll find here. And then references for anything I've used inside the teacher's guide are here at the bottom. All right, I know this is really exciting stuff. I feel like I'm really boring you guys. There are assessments or worksheets, however you want to term them as well.
You should have seen me on Wednesday. I was in rare form, slogging through 2 chapters before getting to the hands-on part.
These are all set up the same way. They pretty much all start with a matching. Typically it's vocabulary types of things. I always try to include in the assessment, again, or worksheet, however you want to term that, some type of work with the code that's inside there. There's always some multiple choice, and there's always some short answer, and there's always a little bit of true false. And again, that usually ends up with the short answer at the end. And then of course, the answer key here. For any of the short answers, there is a rubric. If you want to, have some way to assess that in a consistent manner, there's a rubric down at the bottom of these. So there's one of these, again, in that teachers section on the website for each of the tutorials, or there will be soon anyway.
Yes, that's what we will be talking about next.
Yeah, so that is, that's the material that I create. I try to make it as user-friendly for the teacher as I can. Again, trying to look through the lens of maybe a teacher that is kind of like me, who maybe this is not something that they're super comfortable with, but want to dig into and want to be able to present to their students in a, kind of a knowledgeable fashion. So
I think even for a 20-year tech ed teacher, though, just having this and the ability to copy and paste and save the time is great.
Yeah, absolutely. I think having the assessments is really helpful, and having the standards and those and the learning targets, or those student, the student outcomes. So students know as they go through each tutorial, there's a lot of information there. So if you can look at those and really get kids to hone in on what they need to take away from each tutorial, I think it's really helpful. So yeah, that's all I have, Andy, for us.
All right. Thank you, Nicole. That was fantastic.
Yeah. If we have time for those.
So I think you all might be interested in where to find that material. Or should we just shut down the workshop now? All right. Silly joke question. Okay. Let's see. Okay. So I'm going to come back to, let's see. Can you all see me? No, I'm video muted. Okay. Oh, yeah, that's because my camera is still on somewhere. Okay. I'm almost here, folks. Screen share. All right. I'm going to close this briefly and then hopefully be able to get back to the video on Zoom. Okay, so I'm probably back in the thumbnail now. All right, so let's first look at the Learn site to know where to find those resources that Nicole has created for.
You're not on the, we can't see. Now we do.
Okay, yeah, I was having trouble getting the window to move from one screen to another, and finally made it. All right, so when you're at learn.parallax.com, well, right down here is the What's a Microcontroller link, and that takes you to the student materials. But backing out, if you go instead to the educators link right here, then we've got resources for all of the different kits that are used in education. And right at the top is the most recent one, the What's a Microcontroller for Python. And so when you go in here as a student, which is, I'm not logged in right now. And so basically you will see, for example, links to teaching strategy guides, because that doesn't have any questions, exercises, and projects that are answered that we don't want the students to see in it. For anything that we want to make available just to you, well, you've got your educator account, and so you can go ahead and click the login button. And then after you log in, it will look something like this. Bringing up another one here. Okay. So your page will look a little bit different. It won't look exactly like this because this is a web editing mode for changing things in here. But there will be something indicating, hey, you're in teacher mode now. And now when you enter learn.parallax.com and then click educators and select What's a Microcontroller with Python resources, notice that instead of it being locked and saying, hey, you got to log in, the assessment materials that Nicole developed for it are right here. And they're currently in zip files. And so you can basically download it. And I'm bringing up the folder it went to. Got to unzip it. And so here is the assessment materials that she did for the electrical measurements chapter. Paste. I don't know where they went. Let's see here. There they are. Okay, so here's a worksheet, and it may be that there are some things that Stephanie has yet to post, but here, for example, is the PDF version of the student worksheets. And I think that that we, I don't know, Nicole, do you know anything about which teacher's guide chapters have been posted yet, or is that just in Stephanie's queue, do you think, at this point?
Yeah, I don't know which one she's posted yet. I just let her know they're finished, and then I don't get message back necessarily about when it gets posted.
Okay, perfect. Yeah, because I'm not seeing a few things that I think we need to make sure are there. So suffice to say, you'll be able to get all your teacher materials from this area, and all you have to do is log in and go in there to get the assessment materials. I'll go back and just show you another example from Cyberbot.
And Andy, everything is done up through the current one that we're working on. So, you know, it should be able to be posted.
Yeah, so Stephanie's got 73 pages of servo document to move to the web, and we'll just make that load even a little heavier with the other documents you've got in the queue. And so we do expect a lot of that to go up next week, though. Let's see. So here is an example from the Cyberbot, which also is a microbit. This is a microbit piloted robot that you write programs for. And so, for example, if you have a microbit and you're using it in the What's Microcontroller kit, you can actually pull that microbit out of the What's Microcontroller kit and insert it into a Cyberbot. And then you will have a similar set of tutorials and a similar set of teacher's guides. So if we go into the assessment material, so this is what it should look like. So each chapter is going to have assessment material. I'm not sure if this particular series has teacher's guides per se, but it does have a much fuller set of assessment material. But there is teacher guide for the What's a Microcontroller part. So that is where to find the parallax material. Now, cyber.org, which funded in part the development of the Cyberscope, is another, oh boy, it went to the other screen, is another source of curriculum that not necessarily yet for the What's a Microcontroller kit, but certainly for the Cyberbot. And I need to get logged in here. Bear with me a second. When Chrome crashed, I lost a few windows that I had ready to show you. Hopefully I'm off screen right now, so you're not seeing me logging in. Okay, now when you log in, and this is available to US instructors only. And so like Parallax, they will check you. So if you reach out to them from your, to sign up from your teacher email, they'll be able to make sure that they're talking with you, a teacher. And their curricula is somewhat more broad in scope. And just as an example, for our series of robots, we have, you know, I showed you that the Cyberbot tutorials and teacher materials. Well, they have a set of tutorials and materials for the Cyberbot, for the BOE Shield bot. That's an Arduino-based version of the same robot, and then a basic stamp based version of the same robot. And so those things are available at cyber.org, which is a free resource to US teachers. And they have many different curricula, a wider scope than Parallax. Parallax focuses on the microcontrollers, the electronics, the robotics, whereas Cyber goes into to a much wider range of different courses that they have curriculum for on their site. And it's a Canvas type of thing once you go in. And going back to the cover page of cyber.org, the way to sign up is this little sign up link in the upper right. And so when you follow that, they will ask for your information. And again, you have to be a US teacher for this resource. Okay, so one last thing at www.parallax.com. So here is, we have several different robots. So one example here is the Cyberbot. Actually, I think I'll go to learn.parallax.com just to show you. Okay, so your students have done electronics with the microbit, and another thing they can do is robotics with the microbit by plugging it into this nice little robot here called the Cyberbot. And this is what it looks like with the microbit right there. And so some of the tutorials between the Cyberbot are common to the What's a Microcontroller. For example, the writing microbit programs that I sent you to before day one. Well, that's right here as a prerequisite for the Cyberbot as well. And there's some really neat stuff. Like here is infrared navigation with the Cyberbot. And so it has little infrared flashlights. Those little black tubes on the front of the robot are infrared LEDs, light emitting diodes, and they behave like little flashlights. And the black tube, and then built up on the breadboard are little infrared detecting eyes. And so they see that reflected infrared. Another fun little thing that can be done when you have in-person classrooms after the advertisement. Skip ad. So microbits have little digital radios in them. And so Ken here is typing, Ken Gracie set this up. He is basically typing in a command to one microbit connected to his computer, and that microbit is broadcasting that by radio to this fleet of robots. And so, so he's broadcasting from this little microbit connected to his computer right there. He's typing into the terminal. The information goes from the terminal to the microbit, out its radio, and then into the fleet's radios. And then there they are executing the various maneuvers that he's typed in. So that's an example of some fun and interesting things you can do with the Cyberbot as an extension of the material we did. And actually, it doesn't even have to be an extension. You could go through that before, after, or in parallel with what we've done in these workshops today.
Andy,
one moment. Sorry, I've got some audio coming from that that YouTube video. So I'm scrambling to try to. Okay. So hopefully I was screen sharing for all that. I was? Okay, so you saw the robots all turning and everything? Okay, perfect. All right, so somebody was trying to get my attention. What was the question?
Andy, yeah, one of the things, we have a lot of like Bobots that are like 15 years old. And you can, if anybody's got stuff like that and you want a little bit more modern, you can just buy the upgrade kit and upgrade them all to Cyberbots. And that's what we're doing this year, actually.
Norman, that is an excellent point. I'm going to take us to parallax.com after I screen share.
Because it's $100 as opposed to what, 250 or 300 or whatever.
Yeah, yeah. So for example, to purchase a new Cyberbot, oopsie, I just landed in our old website. All right. So here we are at parallax.com, and I'll do a quick search for Cyberbot. Cyber::bot. And so here are some choices. So yeah, the complete Cyberbot kit with a microbit included is $250. Without the microbit, you save about $20. And then if you already have a fleet of Bobot or BOE ShieldBot robots, these are the parts you need right here in this conversion kit. And so you can basically take the board that was sitting on top of the robot off and then put the Cyberbot board and the microbit on, and then swap out the battery pack. The old Bobot battery pack is a 4-cell, and this is a 5-cell that is needed for the Cyberbot. And so, yeah, that is definitely an economical way to upgrade your robot fleets.
And you can still use the old Bobot boards. They're They're called, well, they're just the Board of Education, and you can just use those and write programs on them and do other stuff too with the old boards.
That's true. And even if you have classes that are using one board or the other, there's basically 4 screws that you would loosen and then unplug three cables, the servo cables and the power. And it's really like a 2-minute swap to go between one board and the other.
Yeah, we upgraded 2 of them last year just to see how it worked. It worked really, really well. It's really simple.
Good. I'm glad for the confirmation. Thank you.
I have another question regarding older version. I have a dozen microbit version 1.
Okay.
Version. What we did this week in the tutorial, can we do the same thing with the version 1, or we have to have a version 2?
Currently, everything in the tutorial supports both version 1 and version 2. And as a matter of fact, everything. So the Cyberbot and the What's a Microcontroller with the microbit, they all are pretty much version agnostic at this point. So if you have a bunch of version 1s, you can, let's do What's a Microcontroller here on the search.
Because at first glance, it looked like it's compatible. I just want to double check.
It is. Now they're
complex exercises later.
Yeah. So they do all work. I'm hoping that view results will here we go. All right. So this is a What's a Microcontroller class pack that has 12 kits.
You're not sharing your screen, sir.
Oh, thank you. Let's see here. Zoom, share screen. Okay, there we are. So here is a 12 set class pack that also has some additional modules that can be used in projects, like a motion sensor and I forget what the other one is. I remember hearing what was added and approving it. So we've got the motion, the laser ping. So you can get really high resolution distance measurements up to 3 meters on this, the PIR sensor for motion. So those are additions. And then I believe there's also a continuous rotation servo that was added. I'm looking for that. Laser ping, PIR. Yeah, continuous rotation. So you get a servo that acts like a robot wheel. So you could, for example, use the standard servo that is in the regular part of the kit for steering, some front wheels, and maybe this one for driving a back wheel and a little microbit robot, and then the cables needed for those parts. So
that's like the servo on the Bobots. Those are those kind of continuous servos.
Yeah, except for it's the same small size as the, so like if we follow that link, you'll see that it has the same look. It's just basically, instead of I believe there's the letter B on your servo, which somehow denotes a standard servo that turns to certain angles. And then this R is for rotation, and that it actually behaves more like a motor. Going back to the page, let's see here. Yeah, so we have if you already have a bunch of microbit 1.5s, you can get this kit without the microbit and save some money. There's also replacement packs. This is actually a really good one to paste into the chat. There we go. So now you have this link, and so you can see these kits. And yeah, if there's any other links you want, just let me know. I can send them out. We'll be sending the last video out. I'm not sure whether that will be able to go out tonight or it might wait till Monday, but the YouTube recording and the chat log of this will be coming out soon. And so anybody who came late will be able to catch up. And also you'll just have the link in case you want to refer back to it. Let's see here. So with that said, thanks for continuing on with me, everyone. We went 20 minutes over, so I really appreciate that. Is there, we can open it up for questions and discussion if there's anything else you'd like to go over. Now would be the time. And if it's Friday and we all just want to kind of relax a little bit before it's time to go to sleep, maybe we can just end the session today. And of course, if anybody wants to do a follow-up Zoom, you can just send me an email. You've got my address. We can go over particular things you're interested. Again, I do want more people looking over our material and submitting suggestions. So if you want to become an extra reviewer, it's not a paid position. It's just basically we're hoping for some community feedback. Yes. And so if you're going through it and your students point out to you, hey, look, this part doesn't work, you'll have the link of the working doc and you can actually put a comment in there, and that comment will appear in my email. And then we can look at it and try to figure out a way to improve it.
So I have a couple of questions. I'm going to be exploring the material and trying things, and I have a couple cadets because I'm with the Civil Air Patrol where we're going to be test driving, if you want, because they have some background in electronic themselves, but they're going to be the mentors for the classroom. As much as possible, I'll try to have older or more advanced cadets being mentors for the younger ones, so that there's peer learning at the same time. And we're gonna have our workshops in the spring. So it's our feedback would be given over a few weeks, months. It's not gonna be immediate. And we're working on funds to order the class pack.
Okay.
So for now we have, what you sent, and I'm gonna have to order another one that both cadets have a set to do the testing to work. But so I'm interested in that. And the other thing is I just want to give feedback on the website for the materials. Right now what I've seen was really good. I love the illustration. It's been helping a lot.
Excellent.
Especially as we have a lot of visual learners as much as kinesthetic learners. And one of the big thing is in the environment I work, be it at the Civil Air Patrol or in the Montessori environment, we give some instruction at the beginning, then the students work a lot on their own afterwards. And where we're there as mentors, we go answer questions and monitor and help out, but we are not teaching everything. And the way you set up the website in that section really helps with that part where they can learn a lot on their own.
Excellent.
So really appreciate you taking all the time to do that, and the animated GIF and the little MP4 things really help them with that. So as we get more into that, and like I say, sadly, the big workshop won't be until later, but between spring and summer, we'll have more involvement. And so I'll send you, I have your email address, so I'll send you feedback and questions, or if we find anything, we'll let you know.
Okay, yeah. And also basically, if you're signed up as a reviewer, you'll have the document link. So it's not the web, but it's the Google Doc that was harvested from to go to the web, and the assessment materials and all those things. And it's the ideal place to put it, because every time a comment goes in there, I get an email.
I see that because I use Google Drive, Google
yes.
Workspace
Okay,
a lot.
good.
And even when I have the students or the cadets working in groups, they work in that environment. And I'm always one of the person that is monitoring. So I get all their discussion in between them, and I'm able to step in if I see that they're struggling with something or they're just working between each other. So I really like that common things. And even in administrative level, we've used that when we do strategic plans. And
and in Parallax, we'll have we'll have a group of people all in a Zoom meeting looking at the same document. It's very nice. Yes.
Or we can work on our own time if we have different schedule, because part of what I do is as a volunteer. So it's mainly that. I've been really impressed by the material for us. It's sure that it's growing, it's work in progress, and I realize that you don't have everything. And I look forward to
John, aprende a respetar, okay?
And so I'll contact you. I'm working on funds right now for the workshops, because Civil Air Patrol is a nonprofit, so we have limited budget. So I'm working on grants. So I talked to Ken Gracie also about that, and so we're working on that. And as soon as get that rolling, we'll be implementing this program in the classroom. So.
Okay, well, that is fantastic. Man, thank you so much, Sylvie, for all your feedback. It really does help guide our efforts moving forward. Like, for example, noting that the GIF images assist the visual learners, while some of the hands-on stuff assists the kinesthetic learners, and that kind of thing helps us be sure that we're putting our efforts in the right place. Because the GIFs, for example, they do take more time than just a static drawing. The GIFs are usually 6 or 7 drawings, so it's basically multiplied by anywhere between 7 and really 20 as far as the time it takes to get that image there. But I agree. I really wanted to do that, and that's something that cyber.org helped us out with to make sure that we didn't shirk on it, because we had their help in the way of funding to keep going with that part of the project, which otherwise might have been too expensive given the profit margins that are involved in selling kits like these. And so they helped us out. They made this really great, they got us to make this really great thing with the Cyberscope equipment and the animated GIFs. And so it's more than it would have been, I think, if we'd have just done it as a company on our own. The in concert with, or with the support of cyber.org really made a tremendous difference.
I totally understand. And they have a solid group of educators. I've been working with them for over a couple of years, and it's been really a good source of resources for us also, be it in cybersecurity or teaching, programming and things like that. So
I should mention, would you like to tell them a little bit about the classes they offer?
I don't know. Rosa and Norman, do you know about cyber.org?
Oh yeah, I've been using it for quite a few years, actually.
Yeah.
And
when they were nice, right? When they were still nice.
Yeah. Yeah, their curriculum is really detailed, very, very detailed. And I found that.
And do you do cybersecurity, or do you mostly do the?
I do. I'm a computer science teacher, but I'm an electrical engineer by training. So I like to do a lot of Arduino and microbit and stuff like that. If you're interested, I have a GitHub where I put all my projects. So I've got a microbit section. I've got a Raspberry Pi section, an Arduino section. Python, Java, C++, C#.
If you'd like, if the teachers would like it, would you be willing to share it with the whole group? I could email it out.
Sure. You want me to put it in the chat?
Or, oh yeah, that's even better.
Yeah. No, because we're always looking for
But when the COVID hit, I was told go remote, and I had like 10 minutes warning, and luckily, that particular year, I had a student whose parents retired and moved to Costa Rica, and she wanted to finish my program. My program's a 2-year program, and so she wanted to do the program from Costa Rica. Now we're doing, programming, so it's not like there's a lot of hardware and stuff. So I said, sure, let's do it. So I already had a GitHub set up. So every weekend I would put a new set of stuff up in my GitHub, and then she would do the work and then send it back to me. So when the COVID hit, I already had my GitHub site set up. Can I share the screen? If you want, I can share the screen.
Yeah, let's see if Bonnie is available. Bonnie, are you available to, or first of all, do you have a screen sharing button?
Yes, I do.
Okay, when you hit it, does it let you share the screen?
Yeah.
Oh, okay.
Yes, let me just pop it up here.
I've been wanting to do that, the cyber patrol here in my outreach, but I haven't convinced the parents.
Ah, okay. Yeah, I really hope you do convince the parents, Rosa, because it's kind of an important skill for everybody to learn is
okay, can everybody see my GitHub now?
Yes.
Yes.
We do.
Okay, so here's my repositories, and I've got a microbit on here somewhere. Scratch, here's microbit, and I've got all these little projects. We made robots. I did a summer camp a couple of years ago. I have a piano. I have a one of my favorites is the Marquee remote controller. This is actually I use Fritzing to make stuff. So this was done with middle schoolers. So I have a robot. It's an inexpensive $20 Chinese robot with a microbit in it. And you were talking about the radio. So when you push a button here, it sends out, I think you got 255 channels. But what I found is you actually have to separate them, because I had like 12 kids. And if you don't separate them by at least 10, they interfere with each other. So anyway, this makes the robot turn, go forward. So I have a lot of little projects like this, and you're certainly welcome. It's public, so there's nothing that you could use anything in there. Right now, I know I have several teachers in New Hampshire that are actually using this. I think I have a couple community college teachers that are using my stuff. And I put stuff up every week. In fact, this afternoon, I just put my new Python stuff up. So this is my current course I'm teaching. So these are all my lab exercises and starter code and stuff like that. So anyway, wow. It's a ton of stuff.
This is awesome.
Ton of stuff. So again, there's stuff, anything from scratch to C++. There's stuff on computer architecture, and this is a tech camp I did. This, I believe, was Arduino. We did this. I did this over UNH. And so it's got like all my handouts here for the camp, and I'm not as probably expert at curriculum as you guys, but here's a little micro, basically it's a Arduino. You push a button, it plays Beethoven. So anyway, feel free, just hit the little download button. You can download the whole repository. And I think it's all in pretty good shape. I usually try and make handouts both in Word document and PDF so that you can edit it if you need to, if you want to. So anyway, that's my GitHub, and the address is github.com/edmesa. I'll put that in the chat. Let's see. I think I need to stop sharing.
Oh, to see the chat. Yeah.
I
Hey,
found
well,
it.
thank you so much for sharing that. That's
Let's see.
that's a really amazing public resource you've created.
Yeah, well, you know, you don't reinvent the wheel. You know,
No.
where's my chat? There it is.
Well, plus the
And
advantage is that it's pre-tested, so we already know it's working, and we already have so much time.
Well, I got all my parts. They're all, I mean, all my little projects. I set them out because we're having an open house next week. And I find that having a lot of little toys around, if parents get real impressed with it, so saves me some grief. So you got to have cool stuff for them to play with when they come.
Yeah.
Anyway, we built these robots, I was saying, and then the last day we had Robot Wars. Kids love that. Oh yeah, they took the robots and they could make they took like pencils and made ramming rods and all kinds of stuff. So it was pretty fun.
So Norman, do you have like besides the GitHub, like you said, for instance, that little robot, $20. What is that little robot? Do you have pictures somewhere?
Hold on one
You know
second.
what I mean?
Yeah, hold on a minute here. Let me pull it out. I got right here.
And Andy, I had to take a quick 15 minutes call at 4:45. I hope I muted it. You all did it.
Yeah, well, we didn't hear much. I think there was some initial discussion and then you ended up muting.
Andy, I hope you're not angry because I'm showing these really cheap robots here.
Well, did I disturb you? I'm so sorry.
Oh no, don't worry.
Yeah, it's just a little robot. It's got a microbit in it. And this is the controller we built. So it's got 4 buttons, and you push a button and it makes it go forward, backwards, turn right, turn left. Now, I found that, the microbit for me was kind of, I started using it when it first came out because it was really inexpensive and I could do a lot of stuff with it relatively without, having a lot of hardware, but it was good. So anyway, I built all these little projects. Like I have a piano that we made, and we did this with middle schoolers. So I know that middle schoolers can do this stuff if they're motivated. So, and if they have patience, they have to have patience because breadboarding can be kind of tedious.
Yeah. And
troubleshooting with middle schoolers is a lot of fun. Yeah, that's challenging. Yeah. Any other questions?
Yeah, I'm searching for one of the things we did is that little box that came with the microbit inside it.
You're still recording, by the way, Andy.
Yeah, and that's fine. Let's see here. Share. No, I don't need to share the screen yet. Okay, so the little box that the microbit comes in, well, it makes a good chassis, so you can actually set the board on top of it, and then got to disconnect my setup here. So then the continuous rotation servos, the continuous rotation version of this goes underneath the box.
Oh, you can make your robot.
Yeah.
Nice.
Yeah, actually, you'd only need 2 of them with like a pin on the front of it.
Yeah, and then
this thing has.
Yeah, and then we've got some pretty cool, like since you've got the laser ping sensor in the classroom pack that I mentioned earlier, that you've got some extra goodies for robotics type activities.
Yeah.
So Andy, I had my little first coding club session. I told you right before this class. I can tell being virtual and middle schoolers. Oh my goodness, I hear an echo. I don't know why. But anyways, that I need to get them on this microbit sooner rather than later, right? so that the sessions are, you know, they still, I feel that kids today, it's harder to keep them like engaged and entertained. Maybe, I don't know, they're used to like all the exciting video games.
That. So here's the thing about the microbit that's really important to keep in mind, and that is what I was talking about on the first day, which is like if you go to makecode.microbit.org, there is all kinds of silly things you can do with just the microbit that kids eat up. Like here's your, I'm noticing they're using bananas to tell if you're making electrical contact with the alligator clips. You've got your compass. I'm assuming that this is a potato. Well, I'm not sure. I think they're measuring the temperature of the potato using the Microbit 2.0's temperature sensor. Just a plethora of coding exercises that they can do with the Microbit on its own.
Yeah. There's a
go ahead.
And then like, here's another robot. Here's their milk carton robot.
Yeah, I've seen that.
There's a little treasure hunt game you can make, and I did it with my girls coding club, and you basically make one microbit basically transmit, and the others are receiving, and use the compass, and you hide the microbit somewhere in the building, and then you try and track it down with using the other.
And what all these fun things do is they lay the foundation for the more challenging material that we went over this week.
I get it.
Also, there's a virus game that you can play. I don't know if it's still around, but basically you had one this was before COVID. There's one microbit that's like infected, and then everyone has one that's not infected. You try and figure out who's infected.
So here was my original plan. I was going to start my student, because some of them have never coded, actually a good number. So I was going to start them in Scratch, and then do a little bit of Python, the Carnegie Mellon, CMU, and then do microbit. But I'm thinking I'm going to have to push the microbit like a little, because today's Scratch session, I guess they were engaged, but
well, I found that when you're teaching someone to code, and I've been doing it for quite a few years, and if you put something that says something on the screen, that's one thing, but when you write code that makes something physical happen, that's a whole different level. And because I remember using a Mac many years ago, and the school I went to, I was brand new teacher, and I got an interface. We basically wrote programs on a Mac that turned on a light. And then we said, okay, well, let's make it Flash Morse code. And basically we built from that. And so the whole idea of physical computing is really important, like I said, I started programming in '69, so that's 52 years ago. And then I went and got my electrical engineering degrees, and I continued to code. So I just think coding is a good thing, but if you can do physical computing along with it, that makes it really very meaningful. And we start with 5th graders. That's the age at my school that we start. And I'm in a high school, so what we do is we have these tech fun nights once a month, and we bring in middle schoolers, and we teach them stuff.
So another site, by the way, Rosa, I just pasted in the Make It Code It link that I was showing you. There's another one, or the makecode.microbit.org link. There's another one called Make It Code It. And see that the microbit on its own is kind of like a little microcosm of a cell phone. It's got a display, it's got buttons that you can press, it has its built-in tilt sensor, built-in compass, so your like GPS features of a cell phone. And so young people really seem to, and then it's got the ability to create your own game apps. and like your magic 8-ball, your dice, your name badge. So there's a lot of step counter here by putting the microbit in your shoe. There's just so many different things that they can do with the microbit, and each one provides a coding example. Now, granted, they're not in depth like the things that we did, but they're really good. And there's a whole bunch of them. And so it can keep students engaged and interested. And oh, incidentally, in most cases, there's a MakeCode version. So this is going to be your graphical programming. And then there's a Python version.
Yes.
And so what you can do is you can start with the block programming and then come back around, or have them try it immediately after, depending on what they seem to respond best to, and have them actually try each one. And so they will get exposure to more than one language if that's what you want to do. And again, there's a lot of motivation, like Norman said, the being able to see it and touch it and have something happen that's physical, that's engaging, is very important, especially at the younger ages. And so the microbit is on its own is designed for that. And so what we did in this workshop is kind of picked up after they've been through a lot of this and are ready to, are in the kind of classroom where electronic lessons and, basically the pre-engineering, the learning how to take measurements, learning how to work with units, learning all kinds of other things becomes important.
So Andy, you said you pasted that first URL. I don't see it, or am I on the chat?
Let me see if I got it or not.
Sometimes we forget to push enter.
And maybe I did. Let me check.
Now I see one.
Oh, you know what? I chatted them to Bonnie.
I do that sometimes.
Yeah, because it automatically switches over.
Yes.
Okay.
Because Bonnie sent you a message, and so you answered to that.
Yep. Okay, so there they are.
Encountered. We see it now. One other thing I've encountered is if the students have already experience in doing regular coding, like line coding in Python or Java or something, you take them back and force them to do graphic coding, like MakeCode or Scratch. It's a one-way thing. They can't go back. They hate it when they go back. It's I've had multiple students that they worked with me. We went into JavaScript. We did some web-based mini video game. They were having a blast doing simple things like that. And I left the school for a variety of reasons. I went to work with a different one where I had a more fun environment. And the year after that, the person who took over decided to do Scratch. And part of the students who had done real programming, they just could not stand it because they had been challenged in doing line coding and doing the graphic one that was speculative to them. They really didn't handle it. They didn't feel challenged. And so it's important for you to know your audience. All the hands-on, all the physical programming, I totally agree with everything that Norman and Andy said. But it's also important that you know your personal audience. Do you have students who've never done any programming? You have students who have done some graphic programming, and these ones are going to progress faster, pick up the subject and the challenges you're giving them faster than the others. Do you have anybody who has done real programming? And then these guys are going to be suffering in the class. So it's always also figuring out who you have in front of you, which might be more challenging for you in figuring out how am I going to work with these big diversified classroom where I have different levels and they need different challenges. And that's where I like having resources such as what Parallax is giving us, cyber.org, and now Norman Mesa, thank you.
Yeah.
I prepare in advance where this is the core, this is what I'm gonna do. But if I have a student that needs something more challenging, I have already something prepared for them. If I have a student that is struggling, I really try to identify, do I have more advanced students that can be mentors and be put in a position of assistant teacher, and they are going to go and work with the others. And in that case, it just makes them feel good, even if they're working on a less challenging project, because their challenge now is not to solve the problem, but to help that student learn. So it's
that is really a golden classroom management approach right there.
It's not easy.
Yeah, because yeah, with the varying level of students, typically the approaches are either have something ready so they can work ahead at their own pace, or have them teach the other students, or both. And again, that's like you were saying, it really depends on your audience, what's going to work best. And so, yeah, having those things at your disposal is truly, it can be a lifesaver. And I forgot what I was going to say. I had several thoughts while you were, oh yes, that's right. Okay, so I'm going to screen share real quick. So going back to the language selection based on your students. So you follow one of these tiles and many of them will have different language options. You might see make code Python and even JavaScript. And so, so just know that many of these tiles will have the option of doing the text-based language. And you can also challenge your students to extend whatever example it is that they have worked with. And again, last but not least, that lays the foundation so that when they get to something like the Cyberbot or the What's a Microcontroller material, they will have had some good experiences with programming the microbit on its own, and it's a familiar entity. And the idea is that these things that we're talking about are for them to go further and do more. And with that, I am going to stop the recording if everybody's okay with that.
Yeah, totally. Yeah, right. And the thing is, so that's for you in your preparation, if you have multiple level, you will choose the tiles, you will choose the tiles that have the graphic programming and the line coding or line programming. I don't know how you call it, that's how I call it. But
it makes complete sense. The text-based coding.
Yeah,
we always call it block programming.
Block programming versus what's the other one?
Textual.
Okay.
Textual.
Text, yeah. Yeah, so it's like text or line. But anyway, so ahead of time, I try to figure out the age group. For example, when I'm with the Civil Air Patrol, my cadets are between 12 to 20 years old. And so I have to look at first the age group to know pedagogy-wise how I'm going to teach. And then I have to figure out their background. So 20 years old, I have some college students. And for example, one of the college students is computer science, machine learning. So guess what? This guy is one of my programming instructor.
Yeah, not surprisingly.
So he's one of my pilot study. I give him the toys. Yep. And I say, here's what we want. So we work together on that ahead of time. We prepare, he explores, he suggests certain things so he can go through the curriculum. And then he becomes actually the instructor. And it works really well. And actually what I did a couple of years ago when with NYSERC, when I got my first microbit, that was a first version. That was not version 2 anyway.
Incidentally, on that note, cyber.org does do online trainings, and they have a microbit training coming up. So if you want to do a microbit only training, joining cyber.org as a US teacher, you could have access to that training.
Totally. And if you've done it, it's always worth going back. I've been to some workshop more than once, because every time you go, you learn more when you're not a specialist. Norman, you've been programming since '69. So for you, you probably get it on the first time. Even though I've been programming since the late '70s. Yes, I'm that old, the white hair there. I am a geologist. So computers are tools for me. They are not my main thing. And so I do know how to do programming, but I don't have the level of expertise that you have. But still, so I go back over and over on those things. But one of the challenge was to do a video game on the microbit. And they used the screen was a 25 little LEDs, and they have 2 buttons, and and they had to work with that to create a mini video game.
Yeah, we made a little Pong game on it once.
Yep.
Where
we did one that's more.
It's hard to play.
More inspired by. Yeah, well, we did one actually that was a maze. So the one that won the prize was a maze. It's a little bit like NetHack, but simplified. So the person goes and there are ghosts, and you have to be careful not to touch the ghosts, otherwise it kills you. Anyway, so
Pac-Man, I love it.
It kind of like similar to that, but it was not limited to that in the way that as you're moving in the maze, your screen is moving on in the maze. And the biggest challenge was memory. They had to to optimize their codes to the maximum.
That is where the microbit 2.0 comes in, because it has more than 3 times as much memory as your microbit 1. So when you asked earlier about 2.0 versus 1.5 or 1.35 or 1.4, I forget what the available ones are. Yeah, all of the 1 digit series have some restricted memory. The 2.0 kind of gives you a little bit more, not a ton more, but it's about a 3x improvement in available memory for your programs.
Which is great for certain things, but on the other hand, for the high school ones who've done computer science or college one, I'm keeping the version because these are optimized to learn to optimize their codes. So it's actually a challenge. So there's limited memory.
So I'm going to stop the recording, but first of all, I'm going to say thanks everybody for coming. We can talk a little bit more, but I just want to kind of do a final spiel, I think. So thanks for coming, everyone. We've been at www.parallax.com, where you can purchase microbit kits, and then the main educational resource that we've been talking about has been learn.parallax.com, which I accidentally went to the user login. Boy, some way to end this. So here we are. And then we've been in the What's a Microcontroller with the Python and the microbit. And these are the student materials. And then the educator materials are over in educators. And thanks everybody for watching. We can stay on and continue talking, but I am going to stop the recording at this point. So thanks for hanging out while I do that.